Hello, everybody. Just in case you all don't know, my name is Mika Tarvainen. I'm representing Kubios, and I will be giving you a short, around half an hour introduction to cardiorespiratory signals. So basically, the basis of these signals, how they can be measured, how they are typically processed. And the presentation will be focusing quite much on heart rate variability because that's the main focus in our company.
Mika, may I just interrupt for a second?
Sure.
I see that Anton has started the Read AI recording, which will generate an automatic recording that's stored on American servers. So please kick out the Read AI.
I actually tried to stop this. I don't understand why it added itself here.
Yeah, it's very aggressive. So I also had it installed once. It's automatically connecting to everything you have in your calendar and does recordings and stores them somewhere and sends invitations to everyone else. So
sorry for that, guys. I think now it stopped. I hope.
Okay.
Okay, so we can continue.
So we have our own recording, which we have control over. I think that's better. Then.
Okay.
Sorry for the interruption. Thanks.
No, good. All right. So let me start by introducing cardiorespiratory signals first, and let's start from the basics. So about heart rate. So this is a measurement that you all must be familiar with. So we measure the heartbeats occurring per minute over time. And this is typically computed by averaging 5 or more consecutive beats. So not beat by beat information, but it's also a rolling average over a certain number of beats. The resting heart rate, typically somewhere around 60 beats per minute. If an adult has a resting heart rate over 100 beats per minute, that starts to be abnormal, indicating tachycardia. During sleep, the heart rate can be as low as between 40 and 60 beats per minute. And athletes, especially endurance athletes, have a considerably lower heart rates than let's say normal adult population. So typically between 40 or 50 beats per minute at rest. The maximum heart rate, on the other hand, it's very much age related. There's one simple formula is that it's 220 beats per minute minus your age in years. But okay, there are many formulas for this, and this is probably not the most optimal one. But just to give you an understanding that the older we get, the maximum heart rate also that you can reach during exercise drops for everybody. Then about heart rate variability. So we are not anymore just looking at the mean heart rate, but we are actually capturing the time intervals between every successive heartbeats occurring over time. And if these are captured from the ECG, we typically detect the R waves from the ECG, and therefore we call these intervals as RR intervals. But we could call them also as interbeat intervals or IBIs if it's captured, let's say, from pulse recordings. The heart rate is constantly regulated by the autonomic nervous system, and the changes that occur from one heartbeat to the other are typically quite small. So we are measuring them really in milliseconds. And this requires accurate measurement tools as well as accurate processing tools to have reliable heart rate variability or HRV analytics. The guidelines currently recommend that you should achieve 1 millisecond resolution in detecting these beat-to-beat intervals. So there's not much room for error in this sense. Something shortly about the autonomic nervous system. So this is the nervous system that continuously, without we acknowledging it regulates certain bodily functions. And one important point that it regulates, it's the blood pressure homeostasis. Basically, that different parts of our body have enough blood, have enough oxygen and nutrients within that blood. And regarding the cardiovascular system, the autonomic nervous system regulates, for example, the heart rate, how fast the heart rate is beating. It regulates the blood veins, so basically how elastic they are, how suppressed the blood vessels are. It also affects the arterial baroreflex, which is one, let's say, key element in regulating the blood pressure also and affecting also the heart rate. So this is about the certain type of baroreceptor cells that are in the arterial walls that detect pressure changes. And if they detect a change in increase in blood pressure, they signal that through the autonomic nervous system that the heart rate should be dropped to prevent the blood pressure to get too high. The autonomic nervous system, we can divide it into sympathetic and parasympathetic branches. And the sinoatrial node, which is located on the wall of the right atrium there, has a specific role because the nerve fibers are connected to that node, and all heartbeats basically initiate from that SA node. In a simplified way, the sympathetic activity, that's elevated when we experience stress, when we need to act, do something, and that increases heart rate and decreases heart rate variability. The parasympathetic activity, basically the opposite, that's activated when we are resting, recovering, and the parasympathetic activity decreases the heart rate and increases heart rate variability. So at rest, without any stress, our heart rate is low and heart rate variability is high. Something about the physiological components that we can detect from the heart rate variability. There are two main frequency components. The low frequency component, that's also seen in the blood pressure. So if we would be measuring blood pressure continuously as a function of time, it's typically close to 0.1 hertz frequency, this component. And it's related to the sympathetic regulation of the blood vein, of the vasomotor tone. The high frequency component, on the other hand, it's linked directly to respiration, and this is also called the respiratory sinus arrhythmia, let's say the healthy arrhythmia that we all have. And the power of this high frequency component reflects parasympathetic activation or activity. So it's good to have a high level of higher frequency heart rate variability. And the ratio between these two components is quite often used as an indication of the balance between the sympathetic and parasympathetic branches of the autonomic nervous system. I have a demonstration here how the respiration affects the heart rate. So you can see on the top, basically the respiration going from inhale phase happening now and then exhale phase. And what you see on the bottom, where you see the RR intervals, is that during the inhale, the RR interval starts to drop, meaning that heart rate increases, and during exhale, the opposite happens. So this is basically the one main component that we see in the heart rate variability. We can see also, if we look at the raw ECG data, basically the amplitude of the ECG is modulated by the respiration. And this is one way to indirectly estimate the respiration. I will show you later some details on that. But okay, let's go to how we can measure cardiorespiratory signals, again focusing on heart rate variability measurements. So I will shortly go through the 3 different modalities. So electrocardiography, that's pretty much the gold standard for this. Photoplethysmography, meaning the optical measurement of the pulse waveform, and then also mention some let's say emerging or newer technologies that can be done. And starting from the electrocardiography, so here we measure directly the electrical activity of the heart. And the electrical activity waveform has some specific waveforms inside it. So we can detect a small positive P wave from the ECG that's related to the depolarization of the atriums of the heart. And then we see a sharp QRS complex, which is related to the ventricular depolarization. So basically when the ventricles are contracting, pushing the blood towards the aorta to circulation. ECG, so it's a potential measurement. So we need at least 2 electrodes, 2 contact points to measure it. In clinical use, the standard is to measure a so-called 12-lead ECG. So then we are looking at the electrical activity. Basically, you can think that from 12 different directions, because we place the electrodes, as shown is on this figure on the bottom right, on different sides of the heart, so that we can measure the potential difference caused by the currents running through the heart from different directions. And if we just want to measure heart rate variability, detect the heartbeat, we typically prefer electrode positions so that we have the electrodes positioned kind of on the opposite sides of the heart's main axis. So for example, the lead 2 having 1 electrode on the, let's say, on the right arm or right shoulder, and the other electrode on the left-hand side of the thorax under the heart. So then we get a sharp, strong R wave amplitude. We can measure the ECG using wet gel electrodes or dry electrodes. Wet gel electrodes basically a little bit more or less sensitive to motion artifacts because there is a gel interface between the electrode and the skin. We can quite easily accomplish the 1 millisecond accuracy through the ECG because the R peaks are fairly easy to detect even during exercise. The sampling rate of the ECG is typically between 200 and 500 hertz. Something about different devices that there are for measuring ECG. There are, of course, clinical or diagnostic ECG devices. These are typically medical devices, typically also utilizing the 12-lead connection. Then there are ambulatory ECG devices like Holter monitors that are designed for recording longer periods of time, typically 24-hour or longer. These are quite often 1 lead or 3 lead, sometimes also 12 lead. There are also handheld ECG devices which are applicable for, let's say, short intermittent measurements. Even, for example, the Apple Watch, you could say that it's a handheld ECG device if you touch your right hand's thumb on the watch and you can take a short ECG recording. Then I listed some heart rate monitors which are suitable and quite often used in different sports and wellness applications. We ourselves integrate quite much with the Polar sensors. So for example, Polar H10, that's a chest strap that you see actually here, that you can measure good quality heart rate variability data, basically in any conditions. MoveSense, another actually Finnish manufacturer of HRV sensors, Garmin has chest straps. Suunto has chest straps. Firstbeat has a, let's say, not a chest strap, but a small device that you can connect with electrodes. And this list is just a mentions few, so there are many options for this type of measurements. The photoplethysmography, the PPG measurement. So this measures the changes in the blood volume optically. So based on the fact that you have an LED that transmits light into the tissue, typically maybe green light is quite often used. The blood absorbs light effectively. So the signal that we observe in the photosensor then is kind of inversely related to the blood volume. So the more blood there is on the tissue under the sensor at a time, the less light is reflected back to the photosensor. The sensor placement, there are several options. You have seen many wrist devices, for example, or all the smartwatches nowadays tend to have the PPG sensor underneath the watch. We have also some sensors that you can wear on the arm, for example. Some sensors in the finger, for example, the ring sensors. Earlobe, also one common place to measure PPG. PPG has, let's say, compared to ECG, much more issues with the artifacts. So, for example, movement artifacts are affecting the measurements much more compared to ECG. If the sensor moves, also if there are movements in the soft tissue under the sensor, that's also causing artifacts. And of course, also if the ambient light gets into the let's say the sensor skin interface, that will also cause artifacts to the signal. PPG altogether, it's also a smooth waveform, so you are not easily able to detect the beat time instant as accurately as you can from the sharp ECG QRS complex. So the interbeat interval accuracy that you can typically reach with PPG is maybe plus minus 5 milliseconds, when from ECG it was 1 millisecond. Sampling rate also doesn't need to be that high for PPG because it's a smoother waveform in any case. This some PPG devices suitable for sports and wellness applications. Again, Cubios integrates with polar sensors. So, for example, the Polar Verity Sense we support already in our application, and with that you can measure the raw PPG waveform, the beat-to-beat intervals also. The SHOSH Rhythm 24 is also one. It's an armband that you can wear. HeartMath has an ear clip sensor. Whoop is also, I think, a wrist device, not armband. And Aura Ring, for example, an example of a ring sensor. But also this list could be continued for quite long. Then something about emerging technologies, or let's say other alternatives for measuring heart rate or heart rate variability. Ballistocardiogram is one interesting technology that we have investigated ourselves also inside our company. So this is based on, let's say, very small micro movements caused by the beating heart. So based on the idea that if you would place an acceleration sensor on the, let's say, on the chest above the heart, you would be lying down, staying still. We can see, as you can see in this figure, we can see the heartbeat times from the acceleration data. The signal to noise ratio, again, it's of course something completely different than from the ECG. So the beat detection is more challenging, but from resting measurements, it seems to be a plausible approach for detecting the heartbeats. Other non-contact heart rate detection approaches, there are quite a few applications detecting heart rate from facial PPG imaging. So basically just camera imaging the face and detecting the pulse waveforms from the skin tone, basically. Also Doppler sensors, so basically you can also detect the small movements caused by the heartbeats. This type of measurements, of course, especially the ballistocardiogram and the Doppler, are very sensitive to motion artifacts, so you cannot really move much, or at least you should be able to compensate it quite accurately then. So suitable, in our opinion, only for resting measurements, not for measuring exercise for sure. Interbeat interval accuracy in its best, I think you can reach similar levels than you can with the PPG, but ECG really stays as the gold standard. Sampling rates for these somewhat similar to the PPG, I would say. Okay, then moving on to processing of the cardiorespiratory signals, and let's start from the beat detection. So this is typically the first step. So you measure the raw ECG waveform data or the raw PPG waveform data. If you want to show heart rate, if you want to do heart rate variability analysis, you need to detect every heartbeat as the first step. In case of ECG, it's then typically a QRS complex detector that you need to apply. For example, the Pan-Tompkins is one, let's say, I think still commonly used, quite old, robust detector, or yeah. The bandpass filter typically used in the QRS detectors is between 10 to 30 hertz, so that captures mostly the power within the QRS complex, removing let's say the baseline changes as well as some higher frequency noise from the ECG. The PPG waveform, then it's about detecting the pulse waves. The bandpass filter in these types significantly lower, between 1 and 10 hertz. So basically the 1 hertz just to remove again the baseline changes from the PPG, and the 10 hertz to remove some high frequency noise. Template matching, also one, let's say, typically used approach for detecting the beats. If you have a good template how the QRS complex is expected to look like, or how the PPG one single pulse waveform looks like, you can do that. Or nowadays, I think the deep learning approaches are also outperforming the, let's say, the more traditional detectors. Of course, these new more intelligent detectors require typically quite much data that you need to have, so that you can train your algorithms and have them working in accurate way. Yeah. But once you do the beat detection, the point is that the amount of data reduces significantly. So consider if you have measured ECG at 200 hertz, so that would be 200 samples per second. Once you do beat detection, then you have one value per heartbeat. And that's basically the data that you need to compute heart rate or do HRV analysis. So you don't necessarily need the raw ECG data after this. Noise detection, I would say almost a step in the pre-processing that you should have. So if you detect that some parts of the ECG data or PPG data are clearly corrupted by movement artifacts or some other issues in a way that you cannot really detect the beats from the data, then it's best to just label that, okay, from here to here we had noise. We just need to exclude this part. There's nothing you can do for that. The noise detection algorithms, they can look at the waveform morphology. Does it reflect normal ECG or PPG waveform shapes? You can also look at how are the RR or interbit intervals normal. So is the variability within normal limits, or does it look too abnormal? Movement data is, of course, something that you can use also to guide the noise detection. So if you have an accelerometer inside your device, you can also use that to see that, okay, there's a lot of movement. Maybe the data quality has been compromised. Beat correction regarding heart rate variability is one very important step. So we want to analyze only normal sinus rhythm beats, because those are the ones that tell about the autonomic nervous system. So if there are, let's say, artifacts, we have missed one beat detection, or we have made one, let's say, extra beat detection, or we have one ectopic beat. These must be corrected before the analysis. And I have one example here. So here we have a clean 3-minute HRV data. You can see the heart rate is 49, RMSSD is 56 seconds. So RMSSD just one HRV parameter. If we simulate one ectopic beat, so one premature beat, so we have one shorter followed by a little bit longer interval than normal, the heart rate stays the same, but the RMSSD actually increases by 55%, just having one abnormal beat interval within the 3-minute segment. But once we apply a good beat correction algorithm on the data, we are able to detect and fix that outlier, and the RMSSD also is within the normal or the original level. So just to know that even one single artifact in your data can destroy your HRV results. So it's very sensitive to this. Different HRV analysis methods. I will not really have time to go into this, but let's say we have several time domain methods, several methods that are computed from the HRV spectrum, so the frequency domain methods, and then there are also many non-linear methods. But many ways to characterize the magnitude and, let's say, the morphology or even non-linearity of the variability itself. Respiratory rate estimation, something about that. So it can be indirectly estimated from the ECG or heart rate variability data. Also, if you have a PPG recording, but the ECG-based algorithms have typically outperformed the PPG-based respiration rate algorithms. Kubios has its own algorithm for estimating the respiratory rate, and it actually analyzes two things. So we look at the ECG waveform amplitude in case the recording, if we have the raw ECG data. But in addition to that, we look in any case the RR interval time series. So how the RR interval changes as a function of the respiration. So this is about spectral analysis. And you can see the accuracy here. So it's not perfect, but let's say the error is within roughly 3 breaths per minute in any conditions. In exercise, sometimes even more easier to estimate the respiration than in rest, especially in rest when you are breathing very slowly. It starts to overlap with the low frequency component. All right, moving on to my last slide. So I will just summarize some applications of these cardiorespiratory signals. that we are working on, and for which Kubios has products and solutions. So let me start from let's say stress and recovery monitoring. So this is really where heart rate variability is an ideal objective measurement. So if you would measure yourself, let's say you do a short resting HRV measurement every day, you continue doing that week after week, month after month. So you start to see what affects on your recovery, what increases your stress levels. If you sleep bad, how does it affect in your, let's say, morning recovery level or readiness level? So it provides an objective window for that, to the autonomic nervous system, to the stress and recovery balance of your body. We can estimate fatigue levels. So basically from the same approach that if you monitor your resting heart rate variability, let's say your HRV has been decreased for several days in a row, that starts to be an indication that there's some acute fatigue happening in your body. Or the chronic fatigue, if let's say if the trend towards lower and lower heart rate variability continues for long enough, then it starts to be chronic, and then at least you should be a little bit worried and try to change that direction. Physiological age, one, let's say, wellness parameter, I would say. So we can compare your resting heart rate variability to adult population norms, so norms of different age groups. So we know, for example, that 40-year-old adults typically have a resting heart rate variability at this level. If you make your resting HRV measurement, if you're, for example, an active person living healthy, it might be that your resting heart rate variability is actually quite high, higher than adults typically of your age. Then you get a younger physiological age, just indicating that your heart rate variability, your cardiovascular system is healthier compared to adult population norms. Autonomic nervous system function tests can also tell more detailed information about how your nervous system is functioning. So you can do standardized tests like a deep breathing test or a head-up tilt test where you lie supine and then stand up quickly. So there are also normal values for this, how the nervous systems should compensate, for example, the tilt phase. Heart rate and heart rate variability data also very useful in physiological performance assessments. So we can evaluate training volumes, training intensity from these metrics. So all of you have at least followed, maybe if you are doing exercise, you can check your heart rate. After the exercise, you can check at which heart rate zones you exercised. So that's one thing that you typically do. We can also provide estimates for the ventilatory thresholds. So then you can also see at which metabolic levels you are actually training. We can also estimate oxygen uptake and energy expenditure based on the heart rate and HRV measurements, and also heart rate recovery after the exercise, which is correlated with the let's say physical activity levels or physical fitness. There's some research on that. And finally, HRV guided training is one concept where you kind of combine these two. So if you monitor your recovery levels using, for example, morning resting HRV measurements, you can use that information to optimize your training. So the simple idea is that when your morning HRV tells that your recovery level is good, then you can push harder. So you can train with higher volumes, with higher intensity. When the morning HRV is lower than normal, then you should take it a little bit easier, telling that your body is maybe not fully recovered from the past exercises. And it has been shown that this type of strategy can improve the performance, and typically often that you can reach the same goals with less exercise volumes. Yeah. All right. Sorry for going few minutes over time, but this was all I had in my talk. So I will give the mic to Doug.
Marco, I see that you raise your hand, but we will have the Q&A session after the mic presentation, if that question can wait, or if it's really urgent.
No, it's okay. It's okay.
Great. Okay, so yeah.
Okay, thank you. So good morning, everyone, once again, and let me know. Can you see my screen?
Yeah.
Great. Okay, so my name is Michał Kopczyński. I'm from DSC Digital Company, and today I want to present a presentation about the data compression, intelligent algorithms, and utilization of the computational resources. I will also add some information about the dataset construction for AI inference and AI training that we need in our projects, and we can go through the presentation. So first of all, quick description: what are we doing as a DSC? So as a company, we are delivering the solutions in AI, data analytics, and software development. Our team is around 140 people on board, and we served successfully solutions in over 20 countries across the globe. So here are the quick agenda. So first of all, we'll start with the data compression formats and how to do it smoothly. And then we just go with the intelligent algorithms and the aspect of the computational resources. And the end of the presentation, we will be able to start the Q&A session. So first of all, we need to ask the question: why is data compression necessary, and what are benefits of such compression? So first of all, if we want to run an AI solution on the edge, not sending into the cloud for the inference and getting the results from the cloud, we are struggling a lot of limitations. First of all is the resources, which is kind of obvious that the edge devices have constrained storage and memory, and of course the processing power. Also, what we can gain with usage of data compression is a faster data access. Smaller in size data set, load quicker, so we are saving the time which are very needed for the inference of the AI model. Of course, also we want to provide a solution which will be working in the real time, so that faster data access is necessary. Lower energy consumption, so as it's written, less data transfer means lower computational load, and extended our component life. Low latency, and of course the cost reduction, because the optimized storage lets us to reduce the processing memory, and balance with computational expenses make such solutions more practical. So what are the techniques for the data compression, and what are the formats for the data compression? At DSC, we are using a lot of such formats when working with the HAI and TinyML, as it's well named. nowadays. So first of all, the most important ones from that list, I think, is Parquet and Feeder, because in my opinion, and we are using them a lot at the DC, as I mentioned. There are the columnar storage format and binary columnar format. And we have a few left, SH Avro, Message Pack, Protobuf, AGA5, Pickle, and ORC. What is worth to mention that, for example, the Protobuf format is widely used in the AWS when we have to transfer the data from the edge device to the cloud, or the Pickle when we will be creating an inference algorithm in the Python language. We can use Pickle for serialization and reduce the memory overhead for the datasets. So for that demonstration, for that presentation, I just created a straightforward demo. I just find on the web the data sets that contain the data collected from the wearables, so it's very connected to our goal. As Mika mentioned, the usage of the data set and that sensors was to detect the stress level. So this application is kind of often meeting. That data set includes the measurements from the accelerometer, temperature sensors, HR, and electrodermal activity sensors. And of course, as usually in such cases, we have the timestamps. And what is important in that thing, corresponding labels that indicating the stress of level of each subject. It will be more clear what that means on the next slide. But what is important in that chart, that at the beginning, you can see that the original data set was stored in the comma-separated values format and was around 800 megabytes. After our compression, using the Parquet or the Feeder, we just got the 80 megabytes instead of 800. So it's a huge difference, and we can save a lot of storage and make it simply efficient on the edge. So here's the exemplar dataset annotation. As I mentioned, this is that dataset with the wearables, and as you can see in the yellow column named label, we have the coding. So label encoding is like 2 corresponds to high stress, Y corresponds to normal stress, and 0 corresponds to low stress. And what is important here, that that coding was done by the experts, and was annotated by the experts in that field of analyzing and correlation of the ECG to the stress level. And based on that, when the engineers just acquire such a data set, we are able to teach the neural network hidden patterns that will allow it to make a correct detection in the future without the human intervention. But it's very, very important to get some knowledge, or the experts of the in the field of the annotation, like here, to create a proper AI. Because without data and without the proper annotation, if we have the clear objectives that we want to, for example, detect the level of the stress, we need that correct, proper labeling. Here are other way of the annotation, because we don't have to only base on the feature extracted from the wearables. We can to base on the raw ECG and simply annotate the data using the timestamps. So from the 5 seconds to the 10 seconds, we can see that someone was active and later was resting. So that is giving information to the neural network that can learn from the hidden patterns that's seen the raw signal and analyzing the raw signal when someone is active. So this is other the application. We compress the data. We can fit it on the edge device and store it on the edge device for the AI inference. But how do the models handle the size and performance on the edge? It is very important if we want to omit the usage of the cloud and make the inference straight on the edge and make create the results there. So in shortcut, the neural networks, but also the classical machine learning methods, or even the base rule systems, rely on the data for both training and real-time inference on the edge devices. So when we're training that data collected by the edge devices, when we are training the model using the collected data from the edge devices, it typically requires the large data sets. So the training is typically separated from the edge device. Training on the cloud, but the inference is it uses on the edge device. But we always have to fit it into the memory. So if we compress the data sets, we can also compress the models. Here are the comparison of the model size that can have an application in different cases. So we can notice from the chart that various models from various usages are very different in terms of sizes. So ResNet is the biggest model here. It's around 100 megabytes. The mobile net is almost 20 megabytes. So this is very important to choose the correct one and be sure that we'll be able to fit that. But here are the differences between the models, and we can see kind of correlation in terms of weight, in terms of how very big for the inference time for the 10,000 samples. So ResNet was the biggest one, and the longest time was taken to inference on that samples, but the results was the best. So we are paying for something. Here are the average inference time per sample and the RAM usage to load such model. So mobile net maybe is kind of weaker, but than the ResNet, but we need a lot of less RAM to load it and run it. And this is the first stage because the loading of the model does not equal to the inference. When we want to run the inference, it's typically that we need the half memory of the loading. So usage of the inference, as you can see in the chart, the cost of RAM usage for the loading the ResNet was around the 100, and the inference is for 50 megabytes. So some drawbacks about that models. As I mentioned, choosing a lighter model reduces that memory usage, but we pay for that in terms of accuracy. But running such heavy models and fitting almost the whole memory in the edge device can provide the performance bottlenecks such as overheating or that higher power consumption. So in total, choosing the efficient architecture is a good trade-off, but as I mentioned before, we have also the other solution for that. Simply compress it again. So model compression is kind of different than the data compression because we have different types of the compression. The high level task is simply to fit the large model on a small device and make that large model smaller without the loss of the accuracy. So what are the methods of the model compression. First of all, we have the pruning. Is kind of that we are reducing the connections between the, for example, weights in the neurons in the model, deep learning model. The quantization, that we are converting the precision of the weights of the neural network model to the lower bit representations. Low rank approximation, it kind of classical approach. We just doing the composition of the weight matrices, but maintaining the performance. And one of the hot topics now in the machine learning, deep learning world is the knowledge distillation, where we simply training the models in the manner that the large model is the supervisor, and the smaller one is trying to mimic the behavior of the teacher to get the proper predictions. And to prove to you that it can work, it is the job that we done at the DEC. The SAM model is the segment anything model from Meta that is used for the instance or semantic segmentation, and we need to fit it also to the edge device on the drone. So of course we cannot fit where the model, which size is like almost 2.4 gigabytes. So we decided to use the pruning method and compare the performances between the pruning one and the original one. And what occurs that the average inference time from almost the 2 seconds on the by the image goes to the 0.1 seconds per image, and the model size we reduced from the 2.4 gigabytes to the under the 40 megabytes. And you can see at the images that the performance is kind of the same. Maybe there are kind of little differences, but in total we can assume that they are the same. It's also interesting that the tools for model compression and optimization, that if you will need that in a project, there are a lot of high-end level solutions that we can use straight out of the box, like Amazon SageMaker Neo, TensorFlow Lite, Onyx Runtime, PyTorch quantization. Of course, Amazon usages are paid. The Onyx or PyTorch or TensorFlow for your own experiments is free to use. What is important also, if we will be not able to fit such a model into our edge device even after the compression of the model, we have solution for that. It is named by the AI accelerators, and as it mentioned, is like the specialized hardware that we can just link to our edge device and speed up AI inference by offloading that computation from our edge device to that AI accelerator. And they are used for the edge AI applications very broadly. The most popular ones are, and that's one that we are using at the DEC, are the Coral Edge TPU from the Google, of course, NVIDIA Jetson series, Intel Movidius, and AMD Xilinx Versa AI engines. The first two ones are the most known because they are very generic. The Intel one and AMD are more specific ones. So the first ones are used the most. So to sum up that presentation, what are the key takeaways? First of all, and for our case, where we are working in the H2Train or U-Trains project, it is essential for training of the AI models that we need a well-annotated data set. So our experts from the field of the biosignals analytics or what point to what prediction can help us with creating such a data set to have a reliable AI. Also, it very depends on the application that we'll finally decide to create. For example, for the threshold level, we need the ECG data, and we can annotate that ECG. But maybe we can also want to detect some anomalies. But I think that that topic needs also the second meeting because it will get out of the scope. But the well annotated data set is very important. Raw sensor data alone is insufficient. If we want to predict something which are not anomalies, for at least for the AI usage, and we cannot do it alone at the DAC. So, as I mentioned, we need the help with the dataset annotation. Of course, very important is as I mentioned, the clearly define the prediction goal. This is also crucial to good dataset design and creation, and we have to get the information about the final deployment environment, because the compression of the models, especially, is very dependent on the final deployment environment. So the techniques are different, the results can be different. So we have to know it in advance before we will be starting the training of the AI. So